All right, good afternoon. Thank you for coming. So my name's Alan Gates, and I'm going to talk today a little bit about Hive on ACID. So, let's see. Yep, there we go. All right, so we'll start with some history. As probably all of you know, Hive originally didn't do transactions, didn't do updates and deletes. It did do inserts, but in kind of very specific ways, right? You could insert overwrite an entire partition. You could insert a new partition. You could append data to an existing partition with an insert, though there was no file compaction there, so an insert actually ended up adding a new file, and you had to manually go compact that. Not a huge deal if you didn't do it very often. Definitely a huge deal if you do it on a very regular basis. For the most part, this was fine for where Hive came from, right? With what you're doing is ETL with it, no problem. But there was no way to update or delete rows. There was no way to do certain kinds of inserts, like insert into a table with a values clause. Those things just weren't there. And as Hive started to evolve from an ETL engine to something that people wanted to use for analytics, for data warehousing, these limitations started to become a problem. So why do you need ACID? Why should we add this? We got along without it for years, right? Hive's not exactly a new project. For years and years, Hadoop and Hive just said no to ACID, basically. Just like it was perceived actually as a trade-off that we had made in order to get better performance. And there was some truth to that. It's not completely invalid. But it turns out there's actually value in being able to change things occasionally. Your data is not static. No matter how much you'd like it to be, it's not. Sometimes you bring data in and you realize you made a mistake. You need to restate something, right? Sometimes facts about the world change. A customer of yours might relocate or maybe get a new phone number. Sometimes you have to delete data. Sometimes, hopefully this doesn't happen very often, but occasionally customers might leave no longer be your customer and you're required to delete their data. And the other thing is, the way Hive originally did data was all batch-oriented, right? You would load data in batches, as I said. That's fine, but it has some significant disadvantages. You'd like to be able to load data into Hive as it comes into your system right away, not wait and put it all in a batch, and I'll talk a little bit more about that in a minute. But when people ask us at Hortonworks, why did we start working on ACID? Why did we dedicate resources to this? Really, the best answer is we saw our customers starting to implement this on their own. So at least one, maybe two customers kind of roll in their own solutions to this. And this is something that's hard enough to do inside the system. It's really hard to do from outside the system, right? And it's a lot of work. And when you start to see your users take on that burden to do this yourself, you realize, oh, that probably means we should be thinking about this, right? So we wanted to make this a first-class feature in Hive. So what kind of use cases did we go after here? This is really important to understand because as soon as you say the word transactions, a lot of people's mind jumps straight to OLTP. That is not where we jumped with this. That was not our plan or anything of that nature. Hive is not built to be a classic transaction store, an OLTP type store. And we couldn't, within any reasonable amount of time, we could not have changed that, and that wasn't our intent. But the realization we came to, and the reason we wanted to add this is, just because your focus is on analytics and data warehousing doesn't mean you don't need transactions. You actually still do for some of what I just said. So what explicit use cases were we thinking of when we went after this? What were our goals to enable? And there's kind of four areas here. One is people need to be able to update dimension tables. The example I gave, you have a customer, they move, their physical address changes, you need to update that in your records. Now, some people I know, depending on how you approach slow changing dimensions in your warehouse, you may actually choose to insert a new record and time bound the old one. That's fine, but even then you need to update that old record with a new marker that says, hey, this is no longer the valid one, it's only valid up to this time period in your data, and insert a new one. Or you may choose to just update in place the existing record and forget that your customer used to have a different address. One way or another, you need an update function. Sometimes for compliance reasons, you may be required to delete records. You may either be required to delete certain records after a certain number of days or years, or if a customer or partner or whatever leaves, you may be required to delete that information about them. You need to be able to update and restate large fact tables. We saw customers doing things like, I have somebody comes to my site and buys something, then later they come and buy, maybe they return that product, or they buy something else that complements that, and they want to actually restate that original purchase. So you need to be able to do things like that. Plus, you just need to be able to update the fact that you might have had bogus data get in there. You might have had one server that was generating wrong data, and you want to go back and fix that up in your fact table. So all those were cases where this was useful. And another one, a huge one, is getting data quickly into the system. As I said, Hive used to do data by batch insert. We'd like to be able to stream data into Hive so that it's immediately available, so you don't have to wait. These are the use cases we went after. So just again, to be clear, we're not aiming at OLTP here. We're aiming at making Hive a better data warehousing solution. So what did we do? What did we actually add here? And the first piece that I'll talk about is what changes did we make in SQL itself. This has been in Hive since Hive 0.14, which is over a year old now, like 18 months old now, I think, or close. We added the ability to, say, insert into a set of values. That's not specifically actually ACID, but we went ahead and added that at the same time. We added the ability to update a record with or without, or update a set of records, sorry, with or without a where clause, delete from a table with or without a where clause. This can be done for partitioned and non-partitioned tables. So you can now run these operations over your existing data. Now, there are a number of restrictions on this. First of all, this requires actually support in the storage layer. It's not all in the SQL engine, and so the table must be stored in a format that extends a new interface we added called ACID input format. Currently, the ORC format is the only one that supports that. There is a JIRA out there for work on Parquet to make it support it too. I don't personally work on that one, so I don't have a good estimate on when that will get finished, but it's out there, you can go take a look. The table has to be bucketed, and we have to control the sorting, and I'll get into later why that is. And for now, you have to explicitly mark the table as transactional, and we really did that just to kind of bucket this off. It's a new feature, not everybody's gonna want it, right? We didn't want to force this on people who either were nervous about it or weren't ready for it or just plain weren't expecting it. And so we made this for now where it's an opt-in kind of exercise. At some point in the future, when we feel like this is all, works super well and all the kinks are worked out, we'll probably slowly phase that out to where you don't have to worry about that. The system can automatically mark a table as transactional when these other criteria are met. And you can take existing ORC tables that are already bucketed and you can mark them as transactional. So there is actually an upgrade path with already existing data inside your system. You don't have to just create whole new tables for this. And then the other thing we enabled was this ability to ingest data into Hive from a stream. So as I've said several times now, the old method of this is you would stream data into HDFS. Let's say you're bringing data out of Kafka through Storm, and traditionally you would just drop that in HDFS, and every maybe 15 minutes, maybe every hour, you would take that and insert that as a new partition into Hive. Because you couldn't do that every minute. Hive can't manage a new partition every minute. You'll blow up its metadata if you try to do that. So that was kind of the classic way you handle that. Well, that has the obvious disadvantage that now if my partitions are added every hour, then my users are waiting an hour to see the data, right? Or some portion of an hour before they can see the new data that comes in. Obviously, that's not really what you want, right? You're not excited about an option where it's an hour between the time an event occurs and your users can see that event. So we wrote a new interface as part of this ACID stuff that allows that data to go in transactionally as the table's being read, so that within a few seconds of the record arriving via Kafka or however you're bringing it into your system, it's now visible to readers almost right away. We have connectors for this available for Apache Flume and for Storm. It's an open API. You can write other connectors directly to it. It's not that much work to get that connected. This is actually one of the most popular things we've seen with our new ACID feature is people wanting to use this because they do want to get to the data very quickly. So how did we make this work? HDFS is known to be a write-once file system. You can append in HDFS, but you can't go change things. So how do you update a record when someone says update, change this guy's address from Main Street to A Street? How do you do that? You can't go rewrite the record. You can't delete individual records out of the file if somebody deletes it. So we took the just very traditional approach here. This is actually a problem that has been solved multiple times before by other big data type solutions, because it turns out that even if you do have random access, even if that's an option in your file system, it's so much slower than sequential access that you don't really want to use it. Trying to find that one record to update and just change that bit in millions or billions of records is very expensive. So we take the kind of standard approach there of as updates or deletes come in or new inserts, they're written on the side into a Delta file. And it's then the reader's responsibility to stitch that together at read time and figure out what the right version of that record is, as you will. Yeah.
When you get a full load from a system and a full export from a system, 15 or 20 minutes later there's exported a lot of overlap. Is the comparison to determine the deltas, is that automatically gone, or should it be programmed by yourself?
So I think I'll answer that over the course of the next minute, but if I don't, re-ask it, okay? So what does this look like? What this looks like is as the record's written in, a transaction, when a writer starts a write transaction, they are assigned a transaction ID, which is a sequentially increasing number, right? When a reader goes to start reading, what he is given is a list, a high watermark. This is the top transaction you should ever see. Anything newer than this is not valid because it was not committed when you started reading. And a list of open or aborted transactions. So these are the holes you should ignore, right? Because there might be open transactions still below where that reader started. There might be transactions that wrote something and then were aborted, and so they didn't, that data should be ignored. And then the reader uses that value to stitch it together. So however you get to this data, whether you do it through a SQL query, through an export, through anything else, the reader is actually going to provide you one consistent stream of what this is. Does that answer your question? Okay. So this provides what's called snapshot isolation, meaning that the reader sees that same snapshot for the entire duration of its query. And it also means that there's no exclusive locking. I can have writers writing new data at the same time readers are reading it. I don't have to lock off those areas to avoid collisions between readers and writers. So a question everybody asks, why didn't you use HBase? It's a good question. It's a question we asked ourselves for a while as we designed the system. Should we just use HBase for this? It does have some some good natural fit, if you will. HBase already handles compactions. Obviously, we're going to have to handle compactions, and I'll get to how we do that in a minute. But I just said we're writing these things on the side in a Delta file. You all know that that's not going to work forever. We're going to have to handle that somehow. HBase already does. HBase's LSM model is a natural way to think about this problem. So those were good things. Bad things were we needed transactions, and when we started this project 2.5 years ago, there were no transaction managers for HBase. That's actually no longer a true statement, but at the time it was a true statement. And HBase is, the way it stores stuff isn't quite optimal for what we wanted to do. Hfile is column family based rather than columnar based. Because Hive is used a lot for analytics and data warehousing, columnar is a really good way to work, is really what you want, and so that was a little bit of a mismatch there. But the biggest thing is HBase's sweet spot where it's really, really good is point lookups. I want to find this record or this range of records all on this key. What Hive tends to do are mostly full scans of partitions, right? You're not going to usually ask Hive, find me this one record about this one user. If you're using Hive that way, you're probably making a mistake. What you're going to ask Hive is, find me tell me how many users came to my website yesterday that live in this portion of the country and were also there yesterday, right? That's an appropriate question for Hive. That's a question that you're going to have to scan all of today's data and all of yesterday's data to answer. HBase isn't good at those kinds of scans. That's not its sweet spot. So we wanted something that was still going to scan well in this update case. So this is just a demonstration of what I talked about, how the reader needs to stitch buckets together. This shows how that stitching might look. You have a base file with the original data in it, a couple of Delta files there labeled update 1 and update 2 that have in them what operation was done, the transaction ID it was done at, and what row ID. Those three taken together, the transaction ID, row ID, and bucket ID actually taken together form a unique key so that the reader can understand how to merge these together and present one coherent view to the upstream system. So what does this end up looking like in your file system in HDFS? We didn't want to change the way this was laid out in HDFS, obviously, or at least make as few changes as possible. So just as Hive in the past laid this out as /warehouse/database table partition, we didn't change that. All we changed is underneath we added a base directory with a transaction ID, that's what TID stands for there, and a delta with a range of transaction IDs. So what does this mean? This means that you have a base file that has data valid up to whatever this transaction ID. So maybe that's 1,000, meaning information about transactions 0 to 1,000 are in this base file. And then there are Delta files, say somebody comes in, does one update. There'd be a Delta file here with transaction ID 1001 to 1001, and it'll become obvious in a bit why that range might actually be bigger. But that is to tell readers, that allows readers to do early trimming on what files I should and shouldn't read, right? Because they may come in and say, hey, I'm only valid up till transaction 999, so I know I can completely ignore that delta. I won't even put it in my merge set when I start trying to read these files. So as I said, we needed to add new input and output formats for this because we needed support down at the storage layer itself. We created new interfaces called ACID input format and ACID output format. These interfaces expect to be able to communicate the transactional information to the inputs and outputs so that it can get this merged read back or properly record the information on a write. And that information is original transaction ID, bucket ID, row ID. So bucket ID is just which bucket is this in, obviously. Row ID is a unique value inside that bucket and transaction. And we also actually record latest transaction ID so that you can so you can understand the changes a row goes through, basically the different versions of a row. And then the reader uses that information plus the information it was given by the metadata system on what its valid transaction set is to determine what version of the row to return. As I said, ORC implements this and adds that information into the data when it stores it. Okay, so beyond just the storage layer, we needed support up in the SQL layer too. We needed to have a transaction manager. We needed to have some locking stuff done. So we also wrote a transaction manager for this. Now, Hive did have already 2 existing lock managers. One was in memory, which is obviously not durable if, and also doesn't work across clients if you have multiple clients reading the, reading the data. There was a Zookeeper option. There still is a Zookeeper option that requires installation of additional components and that kind of stuff, which we weren't super excited about. And Zookeeper's way of thinking about locks didn't work super well with what we wanted to do because the locking needs to be integrated with a transaction, right? You open a transaction, you acquire a set of locks. When you either commit or roll back that transaction, you need the unlock to be atomic with that. So there needs to be very tight coupling between the transaction system and the locking system. So what we did is we realized, hey, we have a database here, the RDBMS that we use to power the Metastore, which already has ACID characteristics by definition. We can make use of that to store these transaction IDs and these locks and track all that in a way that will satisfy our needs. So we added that ability to the Metastore to support these opening of transactions, opening of locks, or acquiring of locks, sorry. And we use the Metastore to both provide unique ascending values for transaction and lock IDs and to track who has what lock and who should get the lock next and all that kind of stuff. So all that's stored in the RDBMS. So what do we support in the transaction and locking? Right now, all our statements are auto-commit. We don't yet support begin or commit rollback. So if you do an update or a delete, it will automatically commit as soon as it's done. It is ACID compliant in as much as it will either succeed or fail, not halfway. But you can't do a begin and then update, commit. That we don't support yet. As I said before, we have snapshot isolation so that your readers see a consistent view of the data throughout the course of their query. When we do have cross-statement transactions at some point in the future, that will enable users to issue multiple queries, perhaps even the same query multiple times, and be assured of seeing the same version of the data. You can show the transactions that are, administrators can show the transactions that are out there using show transactions. That's just a tool to help them see what's going on in the system. There's a similar show locks command. What kind of locks did we have to add? It turns out we needed, as I said, we didn't need exclusive locks for the reads and writes. So we added 3 types. Shared read for, okay, obviously readers. You can have as many readers as you want. Shared writes for, these are things that can coexist with readers but can't coexist with other writers. So there's times you want to make sure only one system is or only one writer is writing into a partition at a given time, but you find to let other readers go. There are some exclusive locks. These are for DDL operations like drop table, right? I really don't want you to drop the table while I'm reading the table. That's inconvenient and irritating. So that's where we use exclusive locking. Now, where do we need to, what kind of locks are assigned to what kind of operations? It's not necessarily exactly what you might expect. Select and insert both get a shared read. Now, the first time most people look at that, they go, wait a minute, why does insert get a shared read? That's not a read operation. What are you talking about? The reason for that is Hive doesn't support primary keys. So there's actually no possibility of 2 inbound rows conflicting with each other. There's no way that your write can conflict with my write, even if you write exactly the same thing, because Hive doesn't have a primary key, so it doesn't have any reason to say, oh, one of those should be valid and not the other. They're both perfectly valid entries. And so when you do an insert, we only acquire a shared read. You can have as many inserters as you want into a table or partition at the same time. Update and delete do acquire a shared write because we don't want two people updating the same record at the same time. That can cause problems. And as I said before, drop, insert, overwrite, those sorts of things requiring exclusive lock. Okay, so the next piece you have to build, if you're going to have all this, is you have to clean up after yourself, right? You can't just create Delta files forever and be happy. Each transaction or batch of transactions in a streaming case creates a new Delta directory. So as I said, you come in to do an update, that's going to create a Delta directory. If in the streaming case, you actually open a batch, what's called a batch of transactions, do a whole set of commits, and then you close the batch, that's all going to get written into one Delta file. If you have too many files, a couple things will go wrong on you. One, the name node will hate you very quickly. Well, actually, you'll hate the name node because it'll fall over. And two, your read performance will just fall apart because you're doing a fan-in merge on your, when you go to read, and that's fine if you've got 5, 10 files. If you've got hundreds of files and you're trying to figure out, okay, what version of this record should I read, and I'm reading across 100 files, you're just not going to get the performance you want, right? So we have to keep that file count down. We didn't want to put this onto the user. We felt like that was not a good user experience if the user had to somehow fix this behind us. So we wrote a system that automatically compacts the files for you. And this is initiated by the Metastore server, and this is kind of an important point that I think we didn't stress well enough in the documents or when we first talked about this. You actually have to run a Metastore service to make this happen. I would say 80% of the queries I get on the list about, I started using ACID and it works fine except it never get compacted. I always say, did you turn on the Metastore service? And they're like, no. Okay, well, that's why your compactor is not running because you don't have the server running. So we needed an active server to run this from. This isn't something we could run in user space because it has to be able to read files and rewrite them potentially as another user depending on how you have Hive set up and stuff, so it needs to run inside the Metastore service. It is done automatically, though you can manually initiate one if you want to. So there's an alter table compact command that will initiate a compaction. We do a couple different kinds of compactions. What we call a minor compaction, which is where we take Delta files and merge them just down to one Delta. So back to the case where we had a base file and every time an update comes in, we add a Delta file. Maybe you get a bunch of those Deltas, you want to compact those together. That's a minor compaction. So at the end of that, you have one base file, one Delta file that's now going to have a range of transaction IDs that are valid inside that Delta file, right? By default, we run that every time there's 10 Delta directories. You can configure that up or down as it works for you. The other type of compaction is a major compaction. This is where we actually go rewrite the world. So you have a base file, you have a Delta file. As that Delta gets bigger and bigger, pretty soon more and more of the data in your base file is invalid, right? And at some point, it just becomes not reasonable to continue using that base file. So we have a major compaction where we actually go rewrite the base file. We do not pause the world during either of these compactions. All these can be done as reads and writes are occurring, and it's all good. That's actually something we worked really hard to get done, is that you didn't have to there were no hits, no garbage collection pauses in the system. Now, the way we achieve that is when you do a compaction, we actually track who's reading the old versions of those files, and we keep them around until we know those are all those readers, would be readers, all those readers are done. So let's say that you have a base file and a Delta file, and and the system decides to do a major compaction, and there's one reader reading that old base file. The new base file is written. Any new readers will go to that new base file and they'll know to not select the old one. But the system will track that old reader and only clean up the old base file when it's done so that we don't end up having to pause anybody.
Question. How resilient is the compaction? Let's say you have a hardware failure or something. Could you lose data or is
So the question is, how resilient is a compaction? It's done as a MapReduce job, so it has all the resiliency of a standard MapReduce. So one thing that's, I guess, another thing I haven't always explained super well is the compaction is not run inside the Metastore service, it's only initiated by it. So the Metastore service watches what's happening, it decides when a compaction should occur, and then it just launches it as a MapReduce job that either succeeds or fails. And if it fails, it just cleans, erases it, and as with any MapReduce job, that data doesn't ever become valid and seen by end users. If it succeeds, then that becomes the new data and it's there. So we have not seen any cases, well, I'll talk about that in a minute because I'll get to the bug. Oh, look, it's on this slide. Okay, so we rolled this out 18 months ago. As with any new software, it didn't work 100% from day one, which is unfortunate, but I guess true. So what are some issues we saw and what are some fixes we made to those issues? Just to be clear, we're not declaring this GA ready for what's in Hive 1.2 or 2.0. We do believe that by the next releases of Hive on each of the 1 and 2 lines, that we'll have all these major issues addressed. But I just want to be clear with that now. So if you're looking at this and thinking, hey, this looks great, we're all for that. Please think it's great. But just know that at the moment, there's still some rough edges. So what were some issues we saw? We saw a lot of deadlocks in the RDBMS. This actually surprised me. I thought that the way we were using the RDBMS was relatively simple and straightforward and should be a fairly light load for a relational database because we weren't looking at starting thousands of transactions a second. As I said, we're trying to do data warehousing here. We're thinking in the 1s to 10s of transactions a second. That should be very easy for our underlying relational database, right? Well, turned out we were wrong. There's a fair amount of deadlock. We saw some deadlock issues. We had to rewrite some of our SQL to better work with, well, actually we had to back off the isolation levels on our relational database and rewrite our SQL around that to better work with that. We saw some usability issues. When people did get themselves in trouble, they were completely befuddled about how to get out of trouble. What locks were blocking what other users, why were compactions running at all, and if so, were they succeeding? We didn't give users adequate tools to really figure those questions out. We did have show compactions and show locks, but they didn't give really enough information, so we made some improvements there. I think there's still some work to do in that space, but we've at least made it a lot easier to debug and figure out what's going on. We saw some resilience issues. When we first wrote the Storm connector to this, it had an interesting bug where it could go insane and open like 1 million transactions, and that knocked us over flat. Like we had no expectations that there would ever be 1 million open transactions, so we hadn't defended ourselves against that. And well, lo and behold, somebody tried it. So we've improved that. I'm sure there's still some ways to kill this thing if you try hard enough, but we've at least made it a lot better about defending itself in the face of either rogue or just buggy connectors. Initially, the compactor could only run in 1 Metastore instance, which isn't a great answer if you've got an HA setup where you have multiple Metastores, and now all of a sudden you have to have 1 config for 1 Metastore and 1 for another, and if one of them fails, you have to go figure out whether it was the one running the compactor or not. So we solved that. You can now spread the Metastore the compactor across multiple Metastores, and they cooperate properly. We had a few correctness issues. We did have streaming ingestion wasn't enforcing the proper bucket spraying, so you could it didn't interact well with like sort merge join and some other things that depended on the way buckets were laid out. And I started to say before we hadn't lost data on the compactor, and then I remembered this one. We did on this, but it was not because the job failed, it was because the job was poorly written. There was actually a race condition where we could lose data in a compaction. We resolved that. We had problems early on with alter table. If you altered the table and added a column, we just went off the rails, and you couldn't read the table anymore. That's been resolved. The one kind of outstanding one, that's the reason I'm still saying not GA, We do have a lost update issue. If two transactions overlap in a certain way, one of them can stomp the other's update, and there's a Jira, whoop, that's the wrong button. There's a Jira up there, maybe not, for that. And then the last space we saw some issues, and still see some issues, honestly, were performance. There's some work that's been done here to speed things up. We've made it so predicates can be pushed down into the deltas in certain cases. We've gotten much better at efficient split calculations so that your query engine can split the data well. But I think there's still quite a bit of work to be done here. This is still an area of active investment for us. So, what do we need to add? A lot of people have come to us and said, this is really nice, but what I want is merge, right, or upsert, depending on what you call it. The idea here is you'd like to be able to bring in data from your transactional stores, say Oracle or whatever your end store is, and you'd like to bring that in, whatever you're using to ETL your data from your transactional stores to your data warehouse, and you'd like to merge that into a table. Some of those might be inserts, some might be updates, and you'd like to do that in a single pass of the data. Right now, an update, in the way we've built the system, requires a scan of the partition or table. So if you have one update that covers 1 million rows, that's great. It runs in a single read and write. But if you have 10 updates, that's not great. Now you've got 10 reads and writes. The way you solve that is with merge, which is a standard SQL construction or construct. So that's an area, that's kind of the next feature area for us in this, is to make this work, and we want to do this according to the SQL standard. This was added to the SQL standard in 2003, and we'd like to follow that. Future work, what do we need to do going forward? As I said, we'd like to do multi-statement transactions. We'd like to be able to do begin, commit, rollback. We'd like to integrate this well with LLAP. If you don't know what LLAP is, come to either my Hive 2.0 talk tomorrow or to Sergey's LLAP talk tomorrow. Actually, better yet, come to both. And we'll talk through that. We want to lower the user burden. You know, at the beginning with the restrictions, I said you have to bucket it, you can't sort it, you have to mark it as transactional. The bucketing we probably need to keep. Actually, we know we need to keep because it just, Owen's here going like this. Because it just makes the merge so much more efficient at read. But we need to hide that, right? We shouldn't be pushing that burden onto you. The users, the system itself should just manage that. We need to allow users to determine the sort order of the table because taking that over has other implications. And we'd like to remove the need to make it transactional. And then finally, we need to improve monitoring and alerting facilities. One area that we still don't do a super good job at is alerting when things do go wrong. You know, what happens when there are 1 million transactions? Well, we defend ourselves better against that now, but we still don't say, hey, help, I'm in trouble. We just still don't send out alerts when the compactor is failing on every run or something like that, which are things we ought to do. So those are all areas of kind of future investment. That I have 2 minutes left. If there are any questions, there's a mic here, or you can shout and I'll repeat the question. Oh, thanks. Questions? Yes? What's that? When is version 2.1? There isn't a schedule for that yet. So 2.0 has been released. 2.0.1, which is just bug fixes on top of 2.1, has been proposed, but I don't have a time schedule for 2.1. Yes?
So how long is the lock leading? So imagine we have joining of 2 tables.
Mm-hmm.
And yeah, so are they locked till before query is complete or readers are complete?
So yeah, the question is how long does the lock live? The lock lives for the duration of the query. But again, if you're joining, it's just a read lock, so you're not blocking any other operator, except somebody who wants to drop the table or something. So it does live for the duration, but we minimize the kind of pain of having it locked. Mm-hmm. Yes?
So can a transaction be ACID over 2
one replicated clusters, like a DR site? Is that simple?
So question is, can something be an ACID transaction between two clusters? Is that fair?
Like a DR site?
We don't, actually Hive doesn't have any capability right now to query across clusters ACID or non-ACID. So we would have to design how that would work before we could answer whether it would be ACID compliant or not.
It's actually even a little worse than that, because if you are replicating the data between the data centers, we don't deal with that well.
Yeah, we don't, ACID and Hive's replication stuff don't play friendly together yet. That's another area. I guess I should have put that on the slide, but that's another area we need to invest in over time. I think somebody else over here had a question.
Will there be sort of linear performance degradation via cluster increases if you apply ACID transactions?
So will there be a linear degradation of the cluster? It's not, so what we've seen so far is there's no degradation at all to non-ACID operations, right? We don't impact other things at all. We have seen a decent performance penalty on the read times of the tables that are ACID, but it doesn't get worse. It's just a function of the fact that, at least initially, we weren't doing splits well. I don't actually have on the top of my head how much that penalty is now that we've fixed all the split stuff. I think it's in the 10 to 20% range. But it's not, it doesn't like keep going down or anything like that.
We definitely have ideas about how to make it better.
Yeah, we want to keep.
We know there's a couple sets of low-hanging fruit that we are working on addressing. It's getting better.
All right. I think I'm over time, but I'll hang around outside if other people have questions. Thank you very much.